Hi everybody and welcome to yet another video in the Deep Learning for Audio with Python series. This time it's super exciting because we are looking into convolutional neural networks and we'll try to explain how they work on a theoretical level. Right, so what are CNNs? Well, CNNs are a quite advanced type of neural network, and they've been mainly used for processing images. And over time we've found out that they are way better at performing like with images than the equivalents, for example, like multi-layer perceptron architecture. And the great thing about CNNs is that they have at the same time way less parameters than dense layers. So when analyzing images, we have this double advantage. So they perform better and they have less parameters than the multi-layer perceptron. But now you may be wondering, but why is that the case? Well, it turns out that image data is somehow structured. So the pixels are not just like randomly like positions like in an image, but usually there are certain emergent structures. So for example, you have structures like edges, shapes, you have invariance to translation, you have scale invariance. So for example, a square remains a square regardless of how big the square is, right? And in a sense, like what we do with CNNs is we try to emulate the way we see stuff and we perceive like images, right? And by doing so, what we do when we see like stuff, it's basically we extract basic features. So for example, we are able to extract when we see something like vertical bars or horizontal bars. And in a sense, all the different components of a CNN try to learn to extract different types of features. So all of this process in a CNN is done relying on a couple of components mainly. So one is the one that provides the name to CNN. So it's called convolution, and the other one is called pooling. So in the remaining part of this video, we'll take a look at these two processes, these two components, like in somewhat in detail. Okay, so let's start with convolution. So at the center of convolution, we have the idea of a kernel. We can call it a kernel, or you can also call it a filter. And now, over the next few slides, you'll understand why that's the case. But in its simplest way of understanding it, a kernel is no more than a grid of weights, like this, over here. You have a 3x3 kernel with a bunch of weights. And the idea is that we apply the kernel to the image. Right? So we have an image and then we apply the kernel. Now I'm going to specify what this means like mathematically like in a second. But before getting that, I want to give you like an overview like of these kernels and convolutions, right? So the other idea is that kernels like and filters have been traditionally used in image processing. So like for detecting edges, for example, or for creating effects like a blur or things like that, right? But now we found out that in deep learning they are very, very useful for processing images as well. Cool. Okay, so now let's try to understand how convolutions work starting from an image. Now, this is a grayscale image, which basically means that we have a bunch of pixels that can vary between 0 and 255, where 0 is basically black and 255 is white. And so we can take this, the image of this cat, and we can translate it into like this grid of pixels. And these values, which are supposed to be between 0 and 255, represents like the values for each pixel, right? So I should notice here I've used quite like small values, just like, yeah, because it's easier, right? Okay, so now let's move on. So we have this translation from an image to its pixel representation. Cool. So we said that we should apply a kernel to the image, right? So we have the pixel representation of the image, we have a kernel here, and the result of the convolution is itself like an output, which is a grid. And in the case of like the settings that I'm going to use, we're going to get an output that basically has the same size in terms of width and height of the original image over here. Now let's try to understand how convolution works. So what we do basically is we overlay the kernel on top of the image. And so, for example, here you'll see that we are overlaying the kernel on top of like this initial red square here on the image, and we center it around like the center like of the kernel, and here it corresponds like to these values, to this 4 that's highlighted in green. Now, when we do that, we get a value, and the value of the convolution is then input in this like output grid over here, which is basically like at the same index of the original image where we've centered the kernel on, right? So how do we get to a value there? Well, what we do basically is we just apply the dot product having like as the two like vectors, like the image and the kernel itself. For the image, we just like consider all of these values here in the red square, which are like correspondent kind of like to the kernel. So we have like the same number of values there, right? And so what we do, and we should know how to do a dot product, because if you don't remember, you should go just and watch back like my video on linear algebra, introduction to linear algebra. But basically what we do here is we take each value and from the image and we multiply that for the correspondent value at the same index of the kernel. So like in this case, we have 5 by 1, and then we add to that 2 multiplied by 0, then we add to that 3 by 0, then we add 2 plus 2. Well, I mean, you get the gist. And the last number, like the last value that we have, is this 0 multiplied by -1 over here. Now, when we take all of these like different like expressions and we run the math, we end up with 18, which is the value for this convolution. Now, not 100% sure that 18 is right, because I did things like quite quickly, but yeah, you can try that out and see like if 18 is actually like the right result for this dot product. But regardless, let's assume 18 is correct. Okay, so we'll take that 18 and we'll just slam it in here in the output grid over here. Right, so how do we continue here? Well, it's quite simple, because now we slide the kernel on the image here, and we slide to the right, and now we center the kernel on this like index here with the one highlighted in green in the image, right? And we redo the dot products and we get 10. We move on, we slide and we get like another value, and it's -3. We slide again and we get 5. Now we go down, right? We go down 1 and we go back to the start, and we have like another value, and we continue like this until basically we can arrive at all the numbers for like this square here, like highlighted in green. Now I've left question marks because I didn't want to do like the calculation, but this is a great way for you to practice with convolution. So you can just like run the numbers there and and write perhaps like the results like in the comments, right? But you may see that there's an issue here, right? Because we have the values of the convolutions just like for this internal square, but the edges over here don't get a number. And why is that an issue? Well, it's why is it an issue like to run that math on the edges, right? And the reason is like quickly explained by just opposing like the kernel on the edges here. So for example, like if we center like the kernel on this 0, 0 like index over here, right? We see that, yeah, we have a part like of this kernel that can't be like applied to like anything really, because we don't have values over there. So what can we do there? Well, there are a couple of solutions. So one, it's kind of super straightforward. We say, wait, so we can't apply the kernel there, so we'll just ignore it. So we'll just ignore the edges, right? Yeah, this is a solution in itself, but the problem with that is that we are we're losing some information, right? So all the edges on the image. The other solution, which is the one that we usually use in deep learning, is applying a type of padding called zero padding. So we come up with an edge, with an artificial edge that has all zeros for the purpose of calculation, right? And so if we do that, then all of a sudden we can calculate, we can perform the convolution also like on the edges of the image, right? And so if we run the calculations also like on the edges, we end up with an output like this, where we basically have the output convolution, which is this grid where like the kernel has been like applied on the image, and we have like all the different results. Again, question marks where I haven't done like the calculation. Cool. Okay, so this is like the basic idea of a convolution. So, but let's think of a kernel and what that is on a semantic level. Well, we can think of a kernel or a filter as a feature detector. So basically we can have a bunch of like different kernels that detect different features. So for example, this kernel here, which has like these ones like on this diagonal here, it's able to detect oblique lines, like diagonals, right? Lines, right? Whereas this type of kernel here could be used to identify vertical lines. And so this is a vertical line detector, right? So now when we have a convolutional neural network, as I mentioned earlier, what we do is we kind of like extract features using these kernels. But now, the great thing about CNN is that we don't hardwire those kernels. Rather, we learn them in the process. So we learn the network itself learns the kernels that it needs to extract in order to perform well in some classification of whatever task we may think of, right? And what does it mean to learn a kernel? Well, what we do basically is we learn the values, the weights of the kernel, all of these numbers here, right? And so when we train a CNN, basically we're training these values in the kernels. Cool. Okay, so when we handle like convolution, we have a bunch of like architectural decisions that we can take to decide which type of convolutions like to use, right? And so here I have like a few things, a few settings that we should specify when we build our architecture. So we should specify the grid size of the convolution, the stride, the depth, and the number of kernels. So let's look into this one by one. Let's start from grid size. Well, this is like very intuitive, right? So the grid size is just the number of pixels for the height and the width of the grid. So in this case, for example, we have a 3 by 3 kernel. And in this case, we have a 5 by 5 kernel, because we have just like five values like for the width and 5 values like for each height, right? So, and obviously, like, let's remember that each like of these guys, basically like it's equivalent like to a pixel. and it analyzes just like 1 pixel when it performs, when we perform convolutions. Right, so you'll notice that I'm using grid sizes with odd numbers. So why is that the case? Well, that's the case because when we have odd numbers, we have a central a value that we can use like as a center, as a reference on the image when we start and run the convolution, right? And so it's usually like you'll see odd numbers. Now there's usually you'll also see square kind of like kernels, but you can potentially use also like non-square, like rectangular grids, right? For example, a 1x3 or a 3x1 kernel. Right, so this was about grid size. Now let's move on to another parameter, stride. So what's the stride? Well, the stride is quite simple. It's the step size that we use for sliding the kernel on the image. Right, so, and the stride itself again is indicated in pixels. So let's try to look at a stride. So here we have our image, and we have a 3x3 kernel that we are applying. Now let's say we have a stride of 1. So we'll just move like this. So we start here, then we'll move this by 1 pixel, and then we'll keep moving by another pixel, and so on and so forth. And so as you can see, we are sliding just by 1 pixel, and this is a stride of 1. Now let's try a stride of 2. This again like is also like quite simple to understand, because like we start in this position and then we jump by 2 pixels, right? Here we go. So this is a stride of 2. Now, you can specify both the horizontal stride and the vertical stride. So when you arrive like at the end of the image, like how much you want to go down in the image, say like by 1 pixel or 2 pixels. And the important thing to understand is that, again, the stride doesn't necessarily need to be like the same for like the horizontal value and the vertical value. We can have a stride of 2 horizontally and a stride of 1 vertically, for example. But usually you tend to use like the same stride for like the vertical part and the horizontal. Cool. So grid size and stride are very important like settings for the kernel. But then we have another one, which is depth. Even though I would say like this comes like it's more constrained. You don't have like much like leverage like there, and you can decide what you want to do. But the basic idea is that if you have a grayscale image, the depth is equal to 1. But if you have a color image that's like, for example, represented in RGB, what that basically means is that image, that each pixel for a color image has 3 values, one for the red, one for the green, and one for the blue color. Right, and so what we do in terms of kernels is we have a kernel. So the kernel like is divided like into 3 like parts, 3 grids. And so we have a grid for the red channel, we have a grid for the green channel, and the third grid for the blue channel. And these are independent, right? So a kernel, in the case of RGB image data, is going to have a 3-dimensional it's a 3-dimensional array, right? So where like the first 2 dimensions represent for example, the width and the height of the kernel, and the third dimension here is the depth. So in this case, in this example, we have a 3x3 kernel, which again we should multiply by 3, because that's the depth. Basically, it's like 3 2-dimensional grids. So one for red, one for green, and one for blue. And so the total number of weights in this case is equal to 27, because it's basically 3x3 by 3, right? Okay, so let's remember, guys. So if we are dealing with RGB data, we're going to have a three-dimensional array as our kernel, where the first two dimensions are the width and the height, and the third dimension is the depth, or it's also called the channel, right? Because in RGB we have 3 channels. Great. So now on to the last setting that we want to look into. So this is the number of kernels, but this is really not that related to like the kernel itself, but it's related to the convolutional layer. Now, a convolutional layer can have, and usually has, multiple kernels. But let's remember that each kernel outputs a single two-dimensional array, and it's that output convolution that we've calculated before, right? And so one question could be, so how many outputs do we have from a convolutional layer? Well, we have as many 2D arrays as the number of kernels, right? So if we have, for example, 5 kernels in a convolutional layer, so we're going to have 5 2D arrays, because we're going to apply each kernel to the input image, and we're going to get 5 separate output 2D arrays, right? Okay, so this is the number of kernels. Now, we've learned quite a lot about convolution. Now we need to look at the other side of the coin. Well, I should say like the other part that's usually used in CNNs. That's called pooling. Now, the most difficult part is behind us, because pooling is quite intuitive. So what pooling does, like at the end of the day, is just like downsampling an image. So it basically shrinks an image. And we do that, in a sense, in a similar manner to convolution, in the sense that we overlay a grid on top of an image. And then in terms of pooling, we have like different options. And the two that are like the most used are like max pooling and average pooling, even though I should say that, yeah, I'd say like in deep learning, like max pooling like is the main one, right? Now, as I said, like pooling is quite intuitive and simple, and it doesn't have like any parameters. So we don't learn anything in terms of pooling. It's a simple like mathematical operation that we perform. Okay, so let's take a look at the different pooling settings that we'll have. And so we have like very simple ones. Again, like there's the grid size that determines like how big like the pooling grid is going to be. We have the stride, again, which is like the step size used for sliding the grid on top of an image. And then we have the type of pooling, so max pooling or average pooling. Okay, so now we know, like we have like an overview of pooling. Now let's take a look at how pooling really works. Okay, so here we'll take a look at a max pooling, where we have a 2x2 grid, and we are going to be using a stride of 2, both horizontally and vertically. Right. Okay, so here we have our 2x2 pooling grid, and so and we just like go like on top of like the input, and so you can image like you can image that this is an image, right? And so here we have like these values, right? And given we are doing max pooling, we just pick the greatest value and we log it in the output grid over here, right? Okay, and so by doing so, we are downsampling the original input, because basically we are just like getting one parameter out of like these 4 parameters. Now, how are we going to continue doing this? Well, if you've like followed like attentively like up until now, so you should know that now I'm just gonna slide the grid with a stride of 2, so I'm moving 2 pixels like on the right, and then again here I'm gonna do the same thing. I'm gonna pick the highest number, which in this case is 10, and I'm gonna log it over here. Right, we continue and we pick 12, and finally we pick 7. Now there's obviously a mathematical relationship between the size of the output the size of the input and the stride, right? And the grid size, right? Okay, so I'm not gonna give you like the general rule, but that you can and you should definitely like understand by yourself. But like in this case where we have a 2x2 max pooling grid with stride 2, you'll see that we are basically halving like the width and the height of the input. So here we have a 4x4 like input grid, and the output grid in this case is a 2x2, right? Okay, so we're basically done. So we know what pooling is. So now we should put together like everything we've learned and understand that a CNN just like uses like, yeah, pooling and convolutions, right? So convolutional layers and pooling layers, and it uses it like by putting more of this like together. So let's take a look at a typical CNN architecture. So here we have the input, which is it's a simple image, right? And then here we have a feature learning I would say like phase, like in the CNN, where we have a bunch of like convolutional layers followed by pooling layers. And so now the network can be like as deep as you want, really. So you can have up to like 50, 100 layers, if not more, right? And after like the feature learning like phase, usually you get a fully connected like layer. So here at the end of like this the feature learning like section of the CNN, we usually like flatten the results. So we move it like from 2D to like a 1D vector, and then we pass that information into like one or more fully connected layers. And in the end, we have a softmax classifier, which provides us with a probability distribution on top of a number of like different categories. So like in this case, we are trying to, like in this particular example, we're trying to classify different types of like transportation vehicles. And so here, softmax is going to give us like values for car, truck, van, bicycle, train, right? Or airplane, for example, right? But let's take a look at this feature learning like segment of the CNN, which is like the most interesting one for our purposes, right? So what happens here is basically that at each convolution, a convolutional layer, basically what we're doing is we're trying to extract features, right? And basically the idea is that at the beginning, towards like the beginning of this feature learning segment, we extract very like low level features. So it could be like edges, but then moving forward, like from edges, we can leverage them, for example, to arrive at shapes. Then going deeper in the network, from shapes, we can arrive at objects. So for example, like a car could be, I don't know, like could be represented, say, by like a few circles, which could be like the tires, and a rectangle, for example, that could be like, I mean, the whole like space like of the car like itself, right? So but this is like important to understand. So we start with low level features, and then while we move from one convolution layer to the next, we abstract higher level features. Cool. And so this is like an intuition of how a CNN architecture works. Cool. Okay, so now you may be wondering, okay, so we've spent so much time on talking about how wonderful CNNs are with images. So what about audio? After all, we are talking about deep learning for audio, like in this series, right? Yeah, but the great thing is that we can think of audio, in a sense, itself as an image, right? So if you guys remember, so what we usually use when we use deep learning, like with audio, we use like spectrograms, we use MFCCs, all of this type of like features. But now we've already like visualized them like as an image. And at the end of the day, these are we can be interpreted as images, right? Both the spectrogram and the MFCCs, right? So in the case of a spectrogram, for example, the different time bins and the frequencies that we have here can be thought of like the X and Y indexes for the pixels of an image. And the amplitude can be thought of the value associated to each pixel, right? So in a sense, a spectrogram is a two-dimensional array, which is really comparable to an image. And the great thing is that a spectrogram and audio in general has, I would say, like structures in them that are like, in a sense, like similar to like images. So like the data itself like is somehow like correlated. It's not like completely like random. And so because of like those structures that we can identify in spectrogram and MFCCs, CNN work really, really well because they're able to extract features while we like apply them, where we apply like convolutions like on the audio data. Right. So now that we have an intuition of how like audio data can be used in CNNs, let's try to look at a specific examples where we look at MFCCs for data, right? And so now the question that I want to ask you is like, given like these settings for these like MFCCs, like and for all of this audio data, what's going to be like the data shape, right? So we have 13 MFCCs. We have a hop length of 512 samples. Now, if you don't remember what a hop length is or an MFCC like is, just like go back to my previous videos where I introduced like all of these audio features. Cool. So we said hop length 512 samples, and then we have the total number of samples in a audio file that we are analyzing. That's conveniently 51,200. Now the question is, what's the data shape that we're gonna expect our CNN to be fed with? And right, so the data shape is 100 by 13 by 1. So let's analyze why that's the case. So here we have 100 different like time windows at which we take 13 values, which are the 13 MFCCs that we are extracting, right? And 100 comes by dividing the overall number of samples in the audio file by the hop length, which is like the sliding window that we use like to calculate the MFCCs. And so again, like these two values are like quite understandable because we understand them saying, yeah, we have 100 time windows at which we've taken the 13 coefficients, the 13 MFCCs. But why do we have a third dimension here? So by 1. Do you guys remember depth? Yeah. So in this case, we have a depth which is equal to 1. So basically, audio data can be kind of like compared to like grayscale images where the depth is equal to 1. So we don't have like RGB-like representation of audio data. It's just like grayscale. We just have depth, just one channel. Right. And so you may be wondering, well, but why do we need to like give like this third dimension? Isn't that redundant? Well, it could be, but again, like CNNs are like supposed to work like with images, and usually images are color images oftentimes, and so they have like channels. So the depth is very important. And right, and in this case, I'm giving you like this data shape here because this is like what TensorFlow is gonna like accept as, yeah, for learning purposes. And so like it's good to get like into that like frame of mind. Wow. So this was intense, but at the same time, now you should have a quite clear understanding of a convolutional neural network, what its components are, what's like the processes that come into place, how like convolutional pooling layers like work and how the overall architecture like is built together. So we should just ask ourselves as usual at the end of these videos, so what's up next? Well, as usual, we'll take all of this theoretical information, and in the next video we're gonna put that into practice. So what we'll do is implementing a music genre classifier, but this time we're gonna be using a CNN. So stay tuned for that. I hope you've really enjoyed this video. If that's the case, just like the video. And if you want to know more and have like more videos like this and never miss one, please consider subscribing. And I guess I'll see you next time. Cheers.